Okay, so this video is about Fermat's little theorem, which says that if we are given any prime p, then the following congruence holds. A to the p is congruent to A modulo p. And here A can be any integer. So the proof which we give is by induction and was first published by Euler. So first we need a lemma. So the binomial coefficient p choose m is congruent to 0 mod p, where p is prime, provided m is between 0 and p. We'll prove this after we've proved Fermat's little theorem. So first we prove it when a is a non-negative integer, and the proof when a is a negative integer is essentially the same. So we start with the base case a equals 0, and clearly 0 to the p is congruent to 0 mod p. And now we assume inductively that a to the p is congruent to a mod p for some a. And we now use the binomial theorem to expand a plus 1 to the p as a to the p plus p choose 1, a to the p minus 1 plus dot plus choose a plus 1. And using this lemma, we see that this expression is divisible by p. Therefore, we have a plus 1 to the p is congruent to a to the p plus 1 mod p. And we can rewrite this as a to the p minus 1 is equal to congruent to 0 mod p, which can be rearranged as or rewritten as you can easily check. And since we have assumed inductively that this is divisible by p, and this whole expression is divisible by p, therefore this is divisible by p. This closes the induction and shows that Fermat's little theorem is true for all positive integers a for whatever prime p we choose. And to prove it for negative integers a, we still use induction, but this time we expand a minus 1 to the p and now you just split it into two cases, p even, and since p is even, p equals 2, or p odd. And that's now the proof proceeds essentially the same way, and so we can just leave that as an exercise. Okay, so now we prove the lemma. So p choose m is equal to p factorial divided by m factorial times p minus m factorial. Now, since m is between 0 and p, none of these two factorials contain the prime number p in their prime decomposition using the fundamental theorem of arithmetic, while this does contain p, and that's an integer, so it's actually divisible by p. Actually, p to the n choose m is divisible by p for some positive integer n, and again we can leave that as an exercise. Okay, so Fermat's little theorem can also be rewritten as a to the p minus 1 is congruent to 1 mod p, p is prime, provided p does not divide a. So that's easy to see because a to the p congruent to a mod p means a to the p minus a is congruent to 0 mod p. So a times a to the 1 is congruent to 0 mod p. And since p does not divide a, and that's an integer, so p does divide a to the p, a to the p minus 1 minus 1. Okay, so why did we rewrite it in this form? It's because Fermat's little theorem actually has generalization. So it can be generalized to the Euler-Fermat theorem, which says that a to the theorem is congruent to 1 mod m, provided a and m are coprime. So phi of m is the number of positive integers less than or equal to m which are coprime to m. So for example, phi of 10 is equal to 4 because the numbers less than 10 and coprime to it are 1, 3, 7, and 9. So incidentally, the Euler-Fermat theorem is actually a special case of an even more general theorem from group theory, which is called Lagrange's theorem, which says that the order of any subgroup of a group divides the order of a group. Maybe we'll do a video another time on that. So now we'll talk about Carmichael numbers. Well, we won't talk a lot about Carmichael numbers in this video, but just to give an idea. So Fermat's little theorem says that a to the p minus 1 is congruent to 1 mod p if p is a prime and p does not divide a. We can ask if a similar equation can hold for all integers a, but where p is not necessarily prime. And it can happen, of course, that p is composite, and then we call p a Carmichael number. So we'll show that 561 is a Carmichael number. It is actually the smallest Carmichael number, but alright. So 561 can be written as 3 times 11 times 17 as its prime factorization. Now, if you check, you will see that 561 is actually congruent to 1 mod 2, and that's 3 minus 1. It is also congruent to 1 mod 10, that's 11 minus 1, and it's also congruent to 1 mod 16, that's 17 minus 1. So if you take any integer a and raise it to 561, then by Fermat's little theorem, that's just congruent to a mod 2. Sorry, that's that's congruent to mod 3, right? That's congruent to a mod 3, as you can easily check. So similarly, a to the 561 is congruent to a mod 11, and a to the 561 is congruent to a mod 17. Now 3, 11, and 17 are pairwise coprime, and so a a to the 561 is congruent to a mod the product, which is 561, for all integers a. And since 561 is not prime, this shows that 561 is actually a Carmichael number.